Hi, we're going to do some examples of using Karnaugh Maps to simplify an expression. In these cases, the Karnaugh Maps are already filled in. This is just some practice to get used to using Karnaugh Maps. And so for each one, what we're going to try to do is to cover the table, cover the table with as big circles as possible and as few as possible. And remember, these circles have to have a number of ones that is either 1, 2, 4, 8, 16, or powers of 2. They have to be powers of 2. And then we'll look at those and see what expressions they correspond to. So we look at this first one. This is a 3-variable Karnaugh map, so it has 8 squares. And we want to look first, do we have a group of 8? No. Do we have any groups of 4? No. Do we have any groups of 2? Yes. And so we have a group of 2 here. And then we have another group of 2, which is right here, and then it wraps around. So that also counts as a group of 2. Now, you do not put more than you need. There are other groups we could do. If we wanted to, we could do, well, it would be wrong for our purposes. This column right here is an implicant, but we don't need it because it does not provide us with the best cover. We want to use the least number of circles as possible. So this top circle, what it represents is these numbers represent x1 and x2, and this number represents x3. So when we look at this square and this square, we want to see what they have in common. So they're on this row, so they both have x3 equal to z in common. And then if we look up here and see what they have in common, they both have x1 equal to 1. x2 is different for both of them, so we're not going to use that one. So this circle corresponds to x1, not complemented because it is equal to 1, and x3, which is complemented because it's equal to 0. Now we're going to look at this bottom circle, so that's this square, and see what they have in common. So this square right here has x1 equal to 1, x2 equal to 0, and x3 equal to 1. So we just look at the intersection of the row and column. This square has x1 equal to 0, x2 equal to 0, and x3 equal to 1. So what do they have in common? They have in common that x2 is 0 and that x3 is 1. So that corresponds to x2 bar, x3. So this is probably the simplest expression that we can get for the function that is represented by this table right here. Okay, so let's do this next one down here. Group of 8? No. Group of 4? Yes, right here. And the bigger your circle, the smaller your term is going to be. For a 3-variable Karnaugh map, a circle of 2 will have expressions that have 2 variables in them. A group of 4 will have an expression that has just 1 variable in it. A group of 1 will have all 3 variables. So we've got this group of 4. Is there anything else that's not covered? Yes, this 1 is not covered. Well, how can we get it? What's the biggest circle we can get it with? The biggest circle we can get it with is right here. So this top row, what do they have in common? Well, notice x1 and x2, they can be anything. The only thing they have in common is that x3 equals 0. X3 equals 0, so that's one of ours. Now, when you have a column, that's easy to tell what they have in common because the side variable will be different, but the variables they have, that'll be this label on the column on top. So x3 is different for both of them, but they both have x1 equal to 1, so not complemented, and x2 equal to 0. So that's complemented. Okay, so now we're going to look at a 4-variable Karnaugh map, and that has 16 squares. And again, we're using min terms. We're looking for sums of products. For sums of products, you use 1s. For products of sums, you'll use 0s. So first we'll look for a group of 16. That would be if they were all filled in. If they were all filled in, that would just be 1. So next, a group of 8. And there's no group of 8, so we're not going to do that one. And next we'll look for a group of 4. Well, there's a tricky group of 4 right here. There's a group of 4 that looks like I did this one wrong in my notes. We have a group of 4 that's right here and wraps around over here. So that gets all of those 1s. So we want to see now, are there any more groups of 4? No. And what 1s do we have left over? We have this one and this one. Well, what's the biggest group we can get them with? The biggest group we can get them with is right here. And remember, we could not, color this one in blue, we could not have done, so I'll do this and then I'll erase it. We could not have done this as a group because it has 3 in it. It needs to have 1, 2, or 4. So then this is good. We've got 2 circles and they're as big as possible. So you want as few as possible and as big as possible. So let's look and see what these 2 have in common. If you have a group of 2 in a 4-variable Karnaugh map, your expression will have 3 variables in it. So let's see. They have x1 in common. It's 1 for both of them. x2 is different for both of them. x3 is 0 for both of them, and x4 is 1 for both of them. So that's that one. Now this group of 4, in a 4-variable Karnaugh map, a group of 4 should be made up of 2 variables. I find them a little harder to do when they wrap around, but it's the same principle. So we're going to look at these 2 and these 2 and see what they have in common. Okay, so the ones over here have x1 equal to 0. The ones over here have x1 equal to 1. So that's not in common. So don't use x1. These over here have x2 equal to 0. These have x2 equal to 0. So we will use that one. It's x2, it's 0, so we put a bar on it. Okay, now let's look at x3 and x4. So x4 is different for both of them, but x3 is the same. So that one will have x3 will be non-complemented, and that will be our expression for this one. Okay, so let's go up to this one right now. And, oh, by the way, just one thing, we'll get to one. So let's look at this one and see, are they all filled in? Is it 16? No. Do we have a group of 8? Yes, we've got a good group of 8 right here. Okay, any more groups of 8? No. What do we have left that we need to cover? We have these ones left we need to cover. So what's the biggest group we can get that encloses those? The biggest group we can get that encloses those, that is, has 1, 2, 4, 8, or 16 in it, is this group right here. That has 4 in it. So even though these ones were already covered, we want to include them because we want to make as big a group as possible. We could not have done the, I'll erase this, we could not have done that because that has 6 in it and not 2, 4, 8, or 16. So now we've got all our ones covered, and we think we have as big a group as possible and as few circles as possible. So let's look at this bottom row. In a 4-variable Karnaugh map, if we have a group of 8, that should only have 1 variable in common. So we'll notice they have all possible values of x1 and x2. So those are not in common. x4 can be 1 or 0, so they don't have those in common. What they have in common is x3 is equal to 1. And so it's not complemented. These 4 right here, it's a group of 4 in a 4-variable Karnaugh map, so that should have 2 variables in it in our expression. So we'll see that they have x1 is 1 for all 4 of them, so that's not complemented. And we'll go over here and see that x4 is 1 for all of them, so we'll do that one. So that one is x3 plus x1, x4. Okay, so now let's look at this next one. It's a little bit tricky, but let's look at it. It's got a group that sometimes is hard to remember to look for. So does it have a group of 8 like the one above it? No, it does not have a group of 8. Does it have a group of 4? And the answer is yes, it does have a group of 4. It has 2 groups of 4. Now I'm going to pause for a minute and let you look at it and see if you can find both of them before I tell you. So I'm going to pause. Okay, so one of them is pretty obvious. One of them, here's a group of 4. The other one is you can count the 4 corners as a group of 4 because they wrap around. So anything that can wrap around can also be a group. So this one wraps around with this one, but it also wraps around with this one. And this one wraps around with that one. Or in other words, the 4 corners are always going to count as a group. So I've got this, 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 and this. And that counts as a group. So there are no more groups of 4. And what ones do we have left over that we have to get? We have to get this guy right here. And we want to get him in as big a group as possible. Well, the only one that we're going to be able to get is this group of 2. Now, notice our groups all overlap. They all have parts of other groups in them, but also each group has a 1 in it that's not included in any other group. If you have a group that all its 1s are included in another group, that's not a prime implicant and you don't need it. You have too many. So let's start with the harder group, the group of 4. That's the 4 corners. So let's look first at x1. x1 here is 0, x1 here is 1, so that's not going to work. x2 is 0 and 0, so that one counts. So x2 bar because it's 0. Now let's look at the x3 and x4. x3 is 0 and 1, so that's not the same. x4 is 0 for both of them, so it'll be that. Okay, now let's look at this other group of 4. x1 is 0 for all 4 of them, and x3 is 1 for all of them. Finally, our group of 2, that's going to have 3 variables in it. x1 is different, x2 is 1, x3 is 1, and x4 is 1. Okay, now let's do this one. Again, we'll look groups of 8. No. Groups of 4. Yes. We have this group of 4. We have this group of 4. And we have this group of 4. And that covers everything. So that's probably the best one. Notice there is another group of 4 right here, but we don't need it because we already have everything covered. So let's say we had done that one first. Let's say we had looked at it and we said, okay, we have this group of 4 and this group of 4, and now we need to get those other 2, and we'll get this group of 4. Well, hey, that works. That's fine. That's another one. It has 3 groups of 4, and it covers everything. So sometimes there's more than one way to do one. I'm going to go back to the first one because that's what I have in my notes so I can check it and make sure it's right. But often there is more than one. So if you have more than one, you want to just check and see if one is better than another. And occasionally, and you'll see this after we do sum of products and product of sums, sometimes a product of sums might be better than a sum of products or vice versa. So to get this, we have this group of 4, this group of 4, and this group of 4. Okay, so this first group right here, what they have in common is x1 is 0 for all of them, and x3 is 0 for all of them. This group right here, I like the column ones because I can just read it off the top. x1 is 1 and x2 is 1. And this group of 4 right here, x1 is 1 and x3 is 1. Okay, now we're going to do our last one is a 5-variable Karnaugh map. And with a 5-variable Karnaugh map, you set them up as 2 4-variable Karnaugh maps. So we have x1, x2, x3, x4 on both of them. And for the map on the right, those all have x5 equal to 1, and these all have x5 equal to 0. So when we're looking for groups, we're also looking for things that can overlap. So like if we took one map, one table, and put it on top of the other table, are there things that match up? And so we can see here that we have this group of 4 and this group of 4 that's on both of them. So that's a group. That's a group of 8. And we have this group of 4 and this group of 4 that's in both of them. So that's a group of 4. We have one more 1 left over, and the biggest group we can get it in is right here. And it's not shared with the other table. So let's see what they have in common. Okay, so for this one right here, this side has x5 equal to 0 and this side has x5 equal to 1, so they don't have x5 in common. So we know about that, so they don't have x5. So let's look at x1, x2, x3, x4. Okay, they all have x1 equal to 0. And if it's true on this side, it's going to be true on this side because these tables are the same. And they all have x3 equal to 1. Now let's look at this group right here. Again, they're spanning 2 tables, so x5 is different. And they all have x1 equal to 1. And they have x3 equal to 0. And x4 equal to 1. Now let's look at this group of 2. They do have x5 in common because they don't overlap with this one. So on the right map, we're saying x5 is equal to 0. So we are going to have to include x5. So what else do they have in common? They have x1 is equal to 1, x2 is equal to 0, x3 is equal to 0, and x5 is equal to 0. And so those are some practice on Karnaugh maps.